Hi, I'm Sebastian. I'm from AMD, and yeah, let me take you on a journey into front-end graphics land. So, where are we? We see our way before us. We start with some intermediate representation already, which is for us either SPIR-V or DXIL. Then we go to the front end that then transforms that into LLVM at some point and runs some transformation on that. Then we give that to LLVM as our backend. And in the end, we get out an ELF. So I'm mostly talking about the front end in the next 10 minutes. So let's look at this piece of LLVM AR. What we see here is a type that's a pointer type to a struct, and the struct contains a 32-bit integer and a float. And if you have such a struct type in your hand, you can call getPointerElementType to get the struct type from pointer type. Now you may notice this is rather old LLVM AR. Now it looks slightly different because there's opaque pointers. So now we just have the pointer. We don't know what's behind that. And it kind of makes sense because in LLVM AR, there was never anything that gave the type behind pointers a meaning. So memory was always untyped. And getElementPointer is just gone. There's no replacement. Or is there? Well, there's some ways around that. So in general, if you had a getPointerElementType call before, you can sometimes replace it. So if you have a global value in your hand, you can call getValueType. And it does exactly the same thing that getPointerElementType did before. Similar, if you have an alloc_a_inst, you can call getAllocateType. Or if you have a getElementPointer instruction, you can call getResultElementType. And there's a few more of these. So far about this, but sometimes, or let's talk about some other cases. For example, in your compiler code, in your frontend code or whatever, you had some function that allocates a value and gives back a value that you know is a pointer type. So if you know it always generates an alloc_a instruction, now that's easy to change. You can just change the function to return now an alloc_a instruction. And if someone wants to know the value that was allocated, it can call getAllocateType from before. If that's not always an alloc_a_inst, sometimes there's a way out. So you can just, instead of only returning the pointer value, return a pair of pointer value and element type of that pointer. Or this is rather specific to graphics frontends where you know a lot and are free to change things. So if you have a function that takes a pointer to an array, for example, you can sometimes change that to take just the array by value. So it's easy to just look at the type of the argument, but it's not easy to look at the type behind the pointer. And inside passes, it's often possible, if you use getPointerElementType before, to just keep a map around of a value mapping to the element type of the pointer, and just replace getPointerElementType with the lookup in the map. So these are all applicable to general LLVM AR. Let's have a look at SPIR-V. So SPIR-V is the intermediate representation used in Vulkan. So let's look at the IR example on the lower left. Here we have a getElementPointer instruction on a pointer that points probably to an array, and we get back the pointer to the element at index 5. Problem is the type in the getElementPointer instruction has no semantic meaning. So any LLVM transformation you run is free to change that to, for example, just an I32. And there is no chance that will survive if you run enough LLVM transformations. However, we may want to use that information later on in our frontend. For example, to emit more efficient IR if we know the stride of the array that we access. So in SPIR-V, the stride has a meaning, and we can kind of rely on that. So what we can do is introduce a custom intrinsic, quote unquote, so not an official LLVM intrinsic, just for the front end, that preserves the array stride. So we have a custom function call that does the same as the getElementPointer instruction. So it gives back the pointer to the element at number 5. but it takes a stride argument and an index argument, and no LLVM transformation that we run will change that. If you ever have the need to add such intrinsics, LLVM dialects may be your friend because it makes it easy to do so. So far about SPIR-V, let's look at DXIL. So DXIL is the intermediate language used by DirectX 12. What is DXIL? DXIL is bitcode from around LLVM 3.7. And here's an example. So we have a struct defined type that is an integer and float. And then we have a function called shader that takes a pointer to such a struct as an argument. So if we now read that code with modern LLVM, what we actually get is just a function shader that takes a pointer type as input. And we don't know anymore what is the type behind that pointer. And that's actually done by the bitcode auto-upgrader. However, knowing the type is important for compilation, neither than DXIL. So what we want is the type information from function signatures, the element types of pointers. And well, the only point where we still know the type is inside the bitcode reader. So what we can do is add a hook in the bitcode reader that saves the pointer element types in metadata. And that's exactly what we do. So what we now have is still the function shader that takes an opaque pointer as an argument, but attached to that we have types metadata. And in the types metadata, we can look up the element type of the pointer, which is the payload struct. So if you look at it from the C++ code, what you had before is get arg operand 0, get type, and then get pointer element type. What we can do now is get the types metadata and the operand there, cast it to a constant, and get the type of that. And there's actually an implementation you can look at in one of the bitcode reader tests. Okay, summarizing, what can we do if we want to switch a frontend to opaque pointers? We can change function signatures in LLVM from passing arguments by pointer to passing them by value. We can use custom intrinsics to preserve additional information that LLVM in general would not preserve. And for DXIL, we can use a hook in the bitcode reader to save argument types and metadata. And if you ever have the need to switch something to opaque pointers, it's always useful to have the code in a state where it can support both opaque pointers and type pointers, so that it's easy to revert and switch around in case you have any regressions. Thanks for listening. If you have any questions, I'm happy to talk to you afterwards. And see you around.